Right now, as you sit here, you are hurtling through space at 67,000 miles per hour, or roughly 107,000 kilometers per hour if you prefer the metric unit. Not gently floating, hurtling. Earth is whipping around the sun so fast that in the time it takes you to finish a single meal, the planet has traveled over 70,000 miles. Stack on Earth's own rotation, the solar system's orbit around the Milky Way, and the galaxies drift through the cosmos, and you are moving at over 1,000,000 miles per hour relative to the oldest light in the universe. You should feel like you're strapped to the roof of the fastest rocket ever built, but you feel absolutely nothing. Not the faintest breeze, not the smallest vibration. Complete, perfect stillness. And the reason why is one of the most profound truths physics has ever revealed. Before we dive in, if you find these kinds of deep explorations into how the universe actually works interesting, a quick like or subscribe really helps this channel grow. It's a small thing, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know from experience, even if you've never really thought about it. You're sitting somewhere right now, maybe on a couch, maybe in bed, maybe at a desk, and you feel still. Completely, unambiguously still. There's no sense of motion. Your body isn't pressed against anything. The air around you is calm. If someone asked you whether you were moving, you'd say no without hesitation. But here's the thing. That answer is wrong. Spectacularly wrong. Right at this moment, you are participating in at least 4 major motions simultaneously. The first is Earth's rotation. The planet spins on its axis once every 24 hours. And if you're standing near the equator, that spin is carrying you eastward at roughly 1,037 miles per hour. That's faster than the speed of sound. If you're at a higher latitude, the speed is lower because you're closer to the axis of rotation. But even at somewhere like London or New York, you're still moving at several hundred miles per hour due to the spin alone. The second motion is the one in the title. Earth orbits the Sun at an average speed of about 67,000 miles per hour. That's roughly 18.5 miles every single second. In the time it took you to read that last sentence, Earth moved about 50 miles through space. Not relative to itself, not in some abstract mathematical sense, but through actual space relative to the Sun. 50 miles, gone, just like that, and you felt nothing. The third motion is the solar system's journey around the center of the Milky Way. Our Sun, along with every planet and moon and asteroid in the solar system, orbits the galactic center at about 490,000 miles per hour. At that speed, you could get from Earth to the moon in less than 30 minutes, and yet our Sun takes roughly 225 million years to complete a single orbit of the galaxy, because the galaxy is that incomprehensibly large. The last time the Sun was at this point in its galactic orbit, dinosaurs hadn't even appeared yet on Earth. The fourth motion is the Milky Way itself, which is falling toward the Andromeda galaxy and being pulled by something called the Great Attractor, a massive concentration of galaxies roughly 150 million light years away. Our galaxy moves through the cosmos at approximately 1.3 million miles per hour relative to the cosmic microwave background, which is the oldest light in the universe and the closest thing we have to a universal rest frame. Add all of these motions together, and you are traveling at extraordinary speeds right now. speeds that make a fighter jet look stationary by comparison. Speeds that would terrify you if you could somehow feel them. But you can't feel them. You feel nothing. And this isn't some failure of your body's sensors. Your inner ear works perfectly well. You can feel the difference when an elevator starts moving. You notice when a car speeds up or brakes. Your body is exquisitely sensitive to motion. So why doesn't it register these cosmic velocities? Why does 67,000 miles per hour feel exactly like zero? The answer begins with one of the most important distinctions in all of physics: the difference between velocity and acceleration. These two concepts sound similar, and people use them interchangeably in casual conversation, but they are fundamentally different things. And understanding the difference between them is the key to understanding why you feel completely still right now despite racing through the cosmos. Velocity is your speed in a given direction. If you're in a car on a highway going 70 miles per hour due north, that's your velocity. 70 miles per hour, northbound. Acceleration is the rate at which your velocity changes. If you press the gas pedal and go from 70 to 80, you're accelerating. If you slam the brakes and drop from 70 to 50, you're accelerating in the negative direction, which we call deceleration. If you turn the steering wheel and change direction while keeping the same speed, you're also accelerating, because acceleration isn't just about speeding up or slowing down. It's about any change in velocity. And velocity includes direction. Here's the critical point. Your body does not sense velocity. Your body senses acceleration. This isn't a limitation. It isn't a design flaw. It's a fundamental feature of how physics works. And you already have a lifetime of evidence for this. You've just never framed it this way. Think about being on an airplane. You board the plane, you taxi to the runway, and then the engines roar and the plane accelerates for takeoff. During that acceleration, you feel it intensely. You're pushed back into your seat. Your stomach tightens. Everything in the cabin that isn't secured slides backward. The force is unmistakable and dramatic. Your body knows, without any ambiguity, that something is happening. Then, the plane reaches cruising altitude. The engines settle into a steady hum. The pilot levels off at about 575 miles per hour, which is roughly 85% of the speed of sound. And suddenly, everything feels normal. You can stand up, walk to the bathroom, pour yourself a glass of water, read a book. The water in your cup sits perfectly flat and still. A pen balanced on the tray table doesn't roll. If someone blindfolded you and placed you on that plane at cruising speed, you would have no way of knowing you were moving. No physical experiment you could perform inside that cabin would reveal your motion. You could bounce a ball, swing a pendulum, measure the flight path of a thrown object. Everything would behave exactly as it does on the ground. The physics inside that cabin at 575 miles per hour is identical to the physics inside a room that's sitting perfectly still. This isn't a trick. It isn't because the plane is somehow shielding you from the speed. 575 miles per hour is genuinely fast. It's fast enough to cross the entire United States in about 4.5 hours. But the speed itself is not what you feel. What you feel is the change in speed. During takeoff, when the plane goes from 0 to 160 miles per hour in roughly 30 seconds, you feel every moment of it because your velocity is changing rapidly. During cruising, when the velocity holds constant, you feel nothing because nothing about your motion is changing. This same principle applies everywhere in your daily experience. Think about riding in a train. A smooth, modern high-speed train traveling at 200 miles per hour on straight, level track feels almost indistinguishable from sitting in a stationary room. The only reason you know you're moving is that you can look out the window and see the landscape sliding past. If the windows were covered, you'd have no way to tell. But the moment the train slows for a station, you feel it. You lean forward slightly. Objects on the table shift toward the front of the car. The deceleration is unmistakable, even though it's gentle. Or think about being in a car on a perfectly smooth highway. At 65 miles per hour on a straight road with no bumps, the ride is comfortable and unremarkable. You might forget you're moving at all. But tap the brakes, and instantly you feel the change. Accelerate to pass someone, and you feel the push. Take a curve, and you feel the sideways force pulling you toward the outside of the turn. Every change in your motion registers immediately and clearly. But the steady, constant motion in between those changes, nothing. Silence, stillness. This is Newton's first law of motion in action, and it's one of the most revolutionary ideas in the history of science. Before Isaac Newton and before Galileo Galilei, most people, including most educated scholars, believed something very different about motion. They followed the ancient Greek philosopher Aristotle, who taught that objects naturally come to rest. A rolling ball eventually stops. An arrow eventually falls to the ground. A cart stops moving when the horse stops pulling. To Aristotle and to common sense, rest was the natural state of things, and motion required a continuous force to sustain it. If nothing was pushing, nothing should be moving. And honestly, this seems perfectly reasonable based on everyday experience. Everything around you does seem to stop eventually. Push a book across a table and it slides to a halt. Kick a ball and it rolls for a while and then comes to rest. Stop pedaling a bicycle and it gradually slows down and tips over. It really does look like motion naturally fades away without a continuous force to maintain it. But Galileo realized something extraordinary in the early 1600s. He noticed that if you reduce friction, objects travel farther before stopping. A ball rolling on a rough surface stops quickly. On a smoother surface, it goes farther. On a very smooth surface, it goes farther still. Galileo saw the pattern. It wasn't that objects naturally stop. It was that something was actively stopping them. Friction, air resistance, the bumps and roughness of surfaces. These were forces acting against the motion, slowing things down. The stopping wasn't natural. It was caused by external forces that happened to be everywhere in our everyday environment. Galileo performed a thought experiment that was absolutely brilliant for its time. Imagine rolling a ball down a ramp. It rolls down one side and up an opposite ramp, reaching almost the same height it started from, minus a little bit lost to friction. Now make the second ramp less steep. The ball still tries to reach the same height, but because the ramp is gentler, it has to roll farther horizontally to get there. Make the second ramp even less steep, and the ball rolls even farther. Now, Galileo asked, what happens if you remove the second ramp entirely and just have a perfectly flat, perfectly smooth surface? The ball will keep rolling forever. It will constantly try to reach the height it started from, but because the surface never rises, it never gets there. It just keeps going. If there were truly no friction, the ball would never stop. This was a revolutionary insight. Galileo was saying that rest isn't the natural state of motion at all. Constant velocity is the natural state. An object in motion stays in motion unless something acts on it to change that motion. And an object at rest stays at rest unless something acts on it to start it moving. Rest and constant motion aren't opposites. They're the same physical state viewed from different perspectives. There is no physical difference between them from the inside. Newton formalized this insight into his first law of motion. An object at rest remains at rest, and an object in motion remains in motion at constant velocity, unless acted upon by a net external force. The key phrase is net external force. Forces cause changes in motion. Forces cause acceleration. Without a force, there is no acceleration. And without acceleration, there is no sensation of movement. Period. Galileo described this principle beautifully in a passage about a ship. He asked his readers to imagine being below deck on a large ship. Bring along some butterflies, some small flying insects. Bring a bowl of fish. Set up a bottle that drips water slowly into a wide-mouthed container below it. When the ship is sitting still at the dock, the butterflies fly equally in all directions. The fish swim around the bowl without favoring any particular side. The water drops fall straight down into the container beneath the bottle. Everything behaves normally. Now set the ship moving at a constant speed across calm seas. Galileo insisted, and he was absolutely right, that nothing changes below deck. The butterflies don't cluster at the back of the cabin. They don't struggle to fly toward the front. The fish don't drift to one side of the bowl. The water drops still fall straight down, directly into the container. You would not be able to tell whether the ship was moving or standing still just by watching these things. The motion of the ship is completely invisible from inside the ship. It has no effect whatsoever on the physics happening in the cabin below deck. This was not an obvious claim at the time. People expected that if a ship were moving, the butterflies would be left behind. The water would drift backward. Everything would behave differently. The fact that constant velocity motion is undetectable was a genuinely surprising discovery. It overthrew nearly 2,000 years of Aristotelian thinking about the nature of motion and rest. Let's make this even more vivid with a thought experiment. Imagine you wake up in a perfectly sealed, perfectly smooth, windowless room. There are no vibrations, no sounds from outside, nothing at all to indicate your surroundings. You don't know where you are. Now imagine someone tells you that this room might be sitting on solid ground in the middle of Kansas. Or it might be in the cargo hold of an advanced spacecraft cruising through deep space at 50,000 miles per hour in a perfectly straight line. Your task is to figure out which one it is. Could you? Could you determine whether you were stationary on Earth or flying through space at extraordinary speed? The answer, according to physics, is no. You could not. There is no experiment you could perform, no measurement you could take, no instrument you could build that would give you the answer. A pendulum would swing the same way in both scenarios. A drop ball would fall the same way. Light would travel the same way. Chemical reactions would proceed at the same rates. Your heart would beat at the same rhythm. Biological processes would unfold identically. Every single physical process inside that room would behave exactly the same regardless of whether the room was stationary or moving at constant velocity. This isn't just approximately true, it isn't true within some margin of error. It's exactly true. It is a fundamental principle of physics, confirmed by centuries of increasingly precise experiments. And this brings us to a realization that sounds simple, but is actually quite deep. If no experiment can distinguish between being at rest and moving at constant velocity, then in a very real sense, there is no difference between them. They are the same physical state. Calling yourself at rest or moving at constant velocity is a choice of perspective, not a statement about physical reality. A person standing on the ground and a person in a spaceship cruising at a constant 100,000 miles per hour are in the same physical condition as far as the laws of physics are concerned. This is a hard idea to accept. We are deeply wired to believe that some things are really moving and some things are really standing still. A car on the highway is the thing that's moving. The road is the thing standing still. Surely that's obvious. But physics reveals something different. Physics reveals that the car is moving relative to the road, and the road is moving relative to the car. Both descriptions are equally valid. Both are physically real. There is no cosmic judge who can point at one and say, that's the one that's truly at rest. Motion is a relationship between two things, not a property that belongs to one thing alone. This is why the phrase 67,000 miles per hour requires context. 67,000 miles per hour relative to what? Relative to the sun? Absolutely. But relative to the center of the Milky Way, Earth is moving at about 490,000 miles per hour. Relative to the cosmic microwave background, the oldest radiation in the universe, Earth is moving at about 1.3 million miles per hour. Relative to a passing photon, a particle of light, Earth is essentially stationary compared to the speed of light. Relative to the person sitting next to you on the couch, you're moving at 0 miles per hour. There is no single correct answer to the question, how fast is Earth really moving? Because the question is incomplete without specifying a reference point. And every reference point gives a different answer, and every one of those answers is equally correct. So let's return to the original question one more time at this level. You don't feel the 67,000 miles per hour because there is nothing to feel. That speed is only meaningful as a relationship between Earth and the Sun. You are not in the Sun's reference frame, you are in Earth's reference frame. In your frame, you and the atmosphere and the oceans and the mountains and the coffee in your cup are all moving together. There is no wind of motion, no force of speed, no vibration of velocity, because velocity doesn't produce any of those things. Only changes in velocity do. And right now, in this moment, the velocity you share with everything around you is not changing. It's constant. And constant velocity, whether it's 0 or 67,000 or a million miles per hour, feels like exactly the same thing. It feels like nothing. It feels like stillness. But we're not done. Because there's something about Earth's motion that we haven't addressed yet. Something that makes this puzzle much deeper than it seems. Earth isn't just moving in a straight line at constant speed. It's orbiting the sun. And orbiting means moving in a curve. And moving in a curve means the direction of motion is constantly changing. And a change in direction is a change in velocity. And a change in velocity is acceleration. Genuine, real, physical acceleration. The kind of acceleration you should, in theory, be able to feel. So why don't you? Why doesn't the curvature of Earth's orbit register in your body the way a sharp turn in a car does? The answer to that question takes us somewhere far deeper than Newton's laws. It takes us to Einstein, to the nature of gravity itself, and to a revelation about what it means to fall. But that's where the story goes next, and it's gonna change how you understand the ground beneath your feet. Part 2. There is no such thing as truly still. We've established something important. Your body detects acceleration, not velocity. Constant motion feels identical to sitting still, and you have a lifetime of experience confirming this every time you fly in an airplane or ride in a smooth train. But now we need to go deeper. Because the idea that motion is undetectable from the inside has consequences that are far more radical than most people realize. It doesn't just explain why you can't feel the speed of a plane, it dismantles the entire concept of truly standing still. And once you understand that, the question of why you don't feel Earth's motion stops being a puzzle and starts being inevitable. Let's talk about inertial reference frames. This is one of the most important concepts in physics, and while the name sounds technical, the idea itself is something you already understand intuitively. You just haven't been given the proper language for it. A reference frame is simply a perspective from which you observe the world. When you're sitting in a train, looking out the window, you have one reference frame. The person standing on the platform watching your train go past has a different reference frame. A bird flying overhead has yet another. Each observer sees the world from their own frame, and each one describes motion differently. From your perspective on the train, the platform is sliding past you. From the platform person's perspective, you're the one sliding past them. Both descriptions are correct. They're just different frames. An inertial reference frame is a frame that isn't accelerating. It's either sitting still or moving at constant velocity in a straight line. No speeding up, no slowing down, no turning. The key property of inertial frames, the thing that makes them so important, is that the laws of physics work the same in all of them. Every equation, every principle, every measurable outcome is identical. You cannot distinguish one inertial frame from another using any physical experiment conducted inside that frame. This isn't just a claim about human perception. It's a claim about the fundamental structure of reality. The universe treats all inertial frames equally. Galileo was the first to recognize this, at least in a clear and testable way. His ship thought experiment showed that the physics below deck doesn't care whether the ship is sailing or docked. Newton built his entire framework of mechanics on this foundation. His laws of motion work the same, whether you apply them on the ground or inside a moving vehicle. But it was Albert Einstein who took this principle and pushed it to its most extreme and revelatory conclusions. In 1905, Einstein published his theory of special relativity. At its core, special relativity rests on two postulates. The first is the principle of relativity, which states that the laws of physics are the same in all inertial reference frames. This was essentially what Galileo and Newton had already established, but Einstein stated it with absolute generality. Not just the laws of mechanics, all the laws of physics, electromagnetism, optics, thermodynamics, everything. No inertial frame is special. No inertial frame is preferred. The universe does not have a favorite perspective. The second postulate is that the speed of light in a vacuum is the same for all observers, regardless of their motion. This sounds harmless, but it leads to some of the most startling conclusions in all of science. Time, dilation, length contraction, the equivalence of mass and energy. But for tonight's discussion, the first postulate is the one that matters most. All inertial frames are physically equivalent. There is no experiment, no measurement, no observation you can make from inside an inertial frame that will tell you your absolute velocity. Because absolute velocity does not exist. Let me say that again because it's genuinely one of the deepest truths in physics. Absolute velocity does not exist. There is no cosmic background, no universal grid, no fixed stage against which your motion can be measured. Motion only exists as a relationship between two things. You can talk about your velocity relative to the sun, relative to the center of the galaxy, relative to the person sitting across from you. All of those are real and measurable. But your velocity relative to nothing, your true velocity in some absolute sense, that concept has no meaning. The universe simply does not contain such a thing. This was a shocking idea when Einstein proposed it, and it remains counterintuitive today. We grow up with the strong impression that some things are really moving and some things are really at rest. The ground feels solid and still. A passing car feels like it's the thing doing the moving. Surely the ground is truly at rest, and the car is truly in motion. But physics says otherwise. The car is moving relative to the ground. The ground is moving relative to the car. Neither one is more truly at rest than the other. Both descriptions are equally valid. The universe doesn't take sides. Before Einstein, many physicists believed there must be some absolute frame of rest. They called it the luminiferous ether, a hypothetical substance that was supposed to fill all of space and serve as the medium through which light waves propagated. If such an ether existed, it would provide an absolute frame. You could measure your velocity relative to the ether, and that would be your real velocity. In 1887, Albert Michelson and Edward Morley performed one of the most famous experiments in the history of physics. They tried to detect Earth's motion through this ether by measuring whether the speed of light was different in different directions. If Earth was moving through the ether, light traveling in the direction of Earth's motion should move at a slightly different speed than light traveling perpendicular to it. The experiment was extraordinarily precise, and it found nothing. No difference at all. The speed of light was the same in every direction, regardless of Earth's motion. This result baffled physicists for nearly 2 decades. It seemed to make no sense. How could the speed of light be the same in all directions if Earth was moving? Einstein's answer was radical. There is no ether. There is no absolute frame. The speed of light is the same for all observers because that's how the universe works. And if the speed of light is constant and no frame is preferred, then our intuitions about absolute motion are simply wrong. Now, let's connect this back to Earth and to you. You are in a reference frame that's moving with the Earth. Everything around you shares this frame. The air in the room, the walls, the floor, the furniture, the coffee in your mug, the blood in your veins, every atom of your body. All of it is moving at the same velocity as the Earth. You are not a stationary person riding on a moving platform. You are part of the platform. You are embedded in it. Every particle of your being has been moving at Earth velocity since the moment you were born. And this is crucial. The atmosphere isn't being left behind as the Earth hurtles through space. The oceans aren't sloshing backward because of our orbital velocity. The air in your room isn't streaming past you at 67,000 miles per hour. Everything moves together. The Earth's gravity holds the atmosphere, the oceans, and everything on the surface in place. All of it orbits the sun as a single unit. There is no relative motion between you and your immediate surroundings. And since your body can only detect relative motion, the differences in velocity between you and the things touching you, there's nothing to detect. You and your environment are locked together in the same frame, traveling at the same velocity, sharing the same motion perfectly. Think about it this way. Imagine you're inside a car with the windows closed, traveling on a perfectly smooth road at 60 miles per hour. The air inside the car is moving at 60 miles per hour too. Your coffee in the cup holder is moving at 60 miles per hour. The seat you're sitting on is moving at 60 miles per hour. Everything in the car is moving together at the same speed. That's why you can take a sip of coffee without it flying into your face. That's why the air inside the car doesn't hit you like a 60 mile per hour wind. Nothing inside the car is moving relative to anything else inside the car. The motion is invisible because it's shared. Now scale that up to the entire Earth. The planet is the car. The atmosphere is the air inside. The oceans, the mountains, the buildings, the people, all of it is riding along at the same speed. There's no cosmic wind hitting us because the air moves with us. There's no force pushing us backward because everything around us shares our motion exactly. From inside this frame, we're at rest. Not approximately at rest. Genuinely, physically at rest, in the only sense that the word rest has meaning in physics. Some people, when they hear this, raise an objection. They say, but surely the sun's frame is the correct one. The Earth goes around the sun, not the other way around. Copernicus settled this 500 years ago. And they're right in an important sense. The heliocentric model, the model that puts the sun at the center with the planets orbiting around it, is a far simpler and more elegant description of planetary motion than the geocentric model that puts Earth at the center. Copernicus, Kepler, and Galileo were absolutely correct to champion it. The sun-centered description is better science, but here's the subtlety that most people miss. Better science and the only correct frame are not the same thing. The heliocentric model is preferred because it's simpler, not because it's the only valid perspective. In Einstein's physics, the Earth-centered description is not wrong. It's just more complicated. You can describe the solar system from Earth's perspective. The math gets messier, but the physics is the same. No frame is more real than any other. The sun doesn't have a privileged claim on being at rest. The sun itself is orbiting the center of the galaxy, which is moving through the local group, which is falling toward the great attractor. If we insist on finding something that's truly still, we never find it. There is no bottom to the ladder. Every object we pick as a reference point turns out to be moving relative to something else. Absolute rest does not exist anywhere in the universe. Now, there's something we need to address that makes this story slightly more complicated, and it has to do with Earth's rotation. Because so far we've been talking about constant velocity motion in straight lines. That's the kind of motion that's truly undetectable. But Earth's rotation is different. Rotation is not straight line motion. When the Earth spins, you're being carried in a circle. And circular motion, even at constant speed, involves a continuous change of direction. A change in direction is a change in velocity, and a change in velocity is acceleration. This acceleration is called centripetal acceleration, and it's directed inward toward the axis of Earth's rotation. So here's the question. If rotation involves real acceleration, shouldn't you be able to feel the Earth spinning? The answer is yes, in principle, and no, in practice, because the acceleration from Earth's rotation is extraordinarily small. Let's do the numbers. At the equator, where the rotational speed is greatest, you're moving at about 1,037 miles per hour. That sounds fast, and it is fast in terms of speed. But the circle you're tracing is enormous. Earth's equatorial radius is roughly 3,963 miles. When you move in a very large circle, even at high speed, the rate at which your direction changes is tiny. The centripetal acceleration at the equator works out to about 0.034 meters per second squared. Earth's surface gravity, the downward pull you feel every moment of your life, is about 9.8 meters per second squared. The rotational acceleration is roughly 0.3% of gravitational acceleration. That's the difference between weighing 150 pounds and weighing 149.5 pounds. You would never notice it. This effect is real though. It's not zero. Precision instruments can measure it. If you placed an extremely accurate scale at the equator and then moved it to the North Pole, it would register a slight difference in your weight. At the poles, there's no centripetal acceleration from rotation because the poles sit on the axis of spin. You're just turning in place, not tracing a circle. So objects weigh very slightly more at the poles than at the equator, partly because of this rotational effect, and partly because Earth's rotation has caused the planet to bulge slightly at the equator, putting equatorial surfaces a bit farther from the center of mass. It's another effect of Earth's rotation that is measurable, called the Coriolis effect. This isn't something you feel directly, but it influences large-scale systems like weather patterns and ocean currents. When air masses move over long distances on a rotating Earth, their paths curve. In the northern hemisphere, moving objects deflect to the right. In the southern hemisphere, they deflect to the left. This is why hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. The Coriolis effect is also the reason large-scale wind patterns exist. The trade winds, the westerlies, the polar easterlies. These patterns wouldn't exist if Earth weren't rotating. But the Coriolis effect is significant only over large distances and long time periods. For a person walking across a room or even driving across a city, the Coriolis deflection is so small, it's completely negligible. The idea that water drains from a bathtub in different directions in different hemispheres because of the Coriolis effect is mostly a myth. The effect exists, but it's far too weak at the scale of a bathtub to overcome other factors like the shape of the basin or tiny residual currents in the water. You need something the size of an ocean current or a continent-spanning air mass before the Coriolis effect becomes dominant. So Earth's rotation does produce real, measurable physical effects, but these effects are subtle. They require precision instruments or enormous scales to detect. In your everyday life, Standing in your kitchen or sitting on your couch, Earth's rotation is as undetectable as its orbital motion. The centripetal acceleration is there, but it's so tiny compared to the overwhelming pull of gravity that it vanishes into the background noise of your sensory experience. There's one more rotation-related phenomenon worth mentioning. In 1851, the French physicist Léon Foucault hung a large pendulum from the dome of the Pantheon in Paris. He set it swinging in a single plane and then watched as, over the course of hours, the plane of the swing slowly rotated. The pendulum itself wasn't changing direction. It was the floor of the Pantheon, and the entire Earth beneath it, that was rotating under the pendulum. The pendulum's swing stayed fixed relative to the distant stars, while the Earth turned beneath it. This was one of the first direct demonstrations that the Earth rotates. It was elegant and simple and completely convincing. But notice what it took to detect the rotation. A very long pendulum, suspended with minimal friction, observed over many hours. Earth's rotation is real, but it's so slow and so smooth that you need a carefully designed experiment running for extended periods to see its effects. Your body has no chance of noticing it. Now, let's address something that's been lurking beneath everything we've discussed so far. It's the deeply held belief, almost a gut instinct, that motion requires a force, that if something is moving, something must be pushing it. And if nothing is pushing it, it must be standing still. This intuition is wrong, and it's been wrong since Galileo showed us why nearly 400 years ago. But it's so persistent and so natural that it's worth dismantling explicitly. In your everyday experience, things do seem to need a push to keep moving. You push a shopping cart and it rolls. You stop pushing and it stops. You pedal a bike and it goes. You stop pedaling and eventually it halts. Every moving object around you seems to require continuous effort to keep it in motion. So, the intuition that motion requires force seems perfectly reasonable. It's been refined by millions of years of evolution. Our ancestors needed to push things, carry things, throw things. Every interaction with the physical world reinforced the idea that motion takes effort. But what's actually happening in all these cases is that friction and air resistance are applying forces that slow things down. The shopping cart doesn't stop because motion naturally fades. It stops because the friction in its wheels and the resistance of the air are actively decelerating it. If you could remove all friction and all air resistance, the cart would roll forever. Not because of some magical property, but because there would be nothing to change its velocity. No force means no acceleration. No acceleration means no change in velocity. No change in velocity means it keeps moving at whatever speed it had when you last pushed it. Indefinitely. This was Galileo's breakthrough, and it remains one of the most important insights in the history of human thought. Motion is not something that needs to be maintained. Motion is the natural state, every bit as natural as rest. An object moving at constant velocity in a straight line will continue moving at that velocity forever, unless something interferes. Rest is just the special case where the constant velocity happens to be zero. This is why no force is required to keep the Earth moving in its orbit. This confuses a lot of people. They wonder, what keeps the Earth going? What force drives it forward? The answer is nothing. Nothing keeps the Earth going. Nothing needs to. Earth has been moving since the solar system formed 4.5 billion years ago. The cloud of gas and dust from which the solar system collapsed was already in motion. As it collapsed, conservation of angular momentum caused it to spin faster. The planets formed from the spinning disk, inheriting its motion. Earth has been moving ever since, and no force has been required to maintain that motion because no force is needed. Motion at constant speed doesn't require a cause. Only changes in motion require a cause. The sun's gravity does act on Earth, but it doesn't push Earth forward in its orbit. It pulls Earth sideways, inward, toward the sun. This inward pull is what curves Earth's straight line path into a closed orbit. Without the sun's gravity, Earth would fly off in a straight line at 67,000 miles per hour, never curving, never coming back. The gravity doesn't provide the motion. The motion was already there. The gravity provides the curve. Think of a ball on a string being swung in a circle. The string doesn't make the ball move faster. It just keeps pulling the ball inward, preventing it from flying off in a straight line. If you cut the string, the ball doesn't stop. It flies away in a straight line at whatever speed it was already moving. The string provided the centripetal force that curved the path. It didn't provide the motion itself. Earth's orbit works the same way. The sun's gravity is the string. It curves Earth's path into an ellipse. But the speed, the 67,000 miles per hour, that's just Earth doing what objects do when no force slows them down. It moves. Constantly. Steadily. Without effort, without fuel, without any engine driving it forward. It moves because that is what objects in motion do when left alone. Understanding this dissolves one of the most common misconceptions about orbital mechanics. People sometimes wonder what would happen if Earth used up its momentum or ran out of energy. But orbital motion doesn't consume anything. There's no fuel being burned. There's no energy being spent. Earth's kinetic energy and gravitational potential energy trade back and forth as it moves slightly closer to and farther from the sun in its mildly elliptical orbit, but the total remains essentially constant. Earth will keep orbiting for as long as the sun exists to provide the gravitational curve, and it will keep moving even after that, sailing off into interstellar space in a straight line when there's no longer a gravitational pull to bend its path. So let's assemble everything we've covered into a single clear picture. You don't feel the Earth moving at 67,000 miles per hour because of several interlocking physical principles, all working together. First, your body detects acceleration, not velocity. Constant velocity produces no sensation. This is Galilean relativity, confirmed by every airplane flight and train ride you've ever taken. Second, there is no such thing as absolute motion. Velocity only exists as a relationship between objects. In your reference frame, the frame you share with the Earth, and the atmosphere and everything around you, your velocity is zero. You are at rest. This is not an approximation. It's physically exact. Third, everything around you shares your velocity. The air, the water, the ground, every atom of your environment moves with you. There is no relative motion between you and your surroundings, and therefore nothing for your senses to detect. Fourth, Earth's rotation does produce a tiny centripetal acceleration, but it's so small compared to gravity, about 0.3%, that it's completely lost in the overwhelming sensation of your own weight. You'd need precision instruments to find it. Fifth, no force is required to maintain Earth's motion. The planet moves because objects in motion stay in motion. Gravity curves the path but doesn't drive the speed. There's no engine, no push, no expenditure of energy keeping us in orbit. All of these facts work together to create the experience of perfect stillness. They conspire, if you want to think of it that way, to make 67,000 miles per hour feel exactly like zero. But we still haven't answered the deepest version of the question, because there's an acceleration in Earth's orbit that is real and not tiny. Earth's direction changes continuously as it curves around the sun. That's centripetal acceleration toward the sun, and it's not negligible. It's small by everyday standards, roughly 0.006 meters per second squared, but it's vastly larger than the noise floor of sensitive instruments. It should, in theory, be detectable, and yet it isn't. Not by any instrument on Earth. Not by the most sensitive accelerometer ever built. This acceleration genuinely exists when viewed from outside from the sun's perspective. But from inside Earth's frame, it completely vanishes. Why? That's the question that stumped physicists for centuries. And the answer, when it finally came, didn't just explain why you can't feel Earth's orbit. It overturned our entire understanding of what gravity is, what falling means, and what it truly means to be accelerating. And the man who figured it out later described the moment of realization as the happiest thought of his life. The year was 1907. Albert Einstein was sitting in his chair at the patent office in Bern, Switzerland. He had already published his theory of special relativity 2 years earlier, reshaping how physicists understood space, time, and motion. But something was bothering him. Special relativity worked beautifully for objects moving at constant velocity. It explained why motion was relative, why the speed of light was constant, why time dilated for fast-moving observers. But it said nothing about gravity, and gravity was the one force that dominated the cosmos. Planets orbiting stars, stars orbiting galaxies, apples falling from trees. Gravity was everywhere, and Einstein's special relativity couldn't account for it. Then, one day, while sitting in that chair, Einstein had a thought. He later called it the happiest thought of his life. He imagined a person falling from the roof of a building. Not a pleasant scenario, obviously, but the physics of it captivated him. He realized that during the fall, the person would not feel their own weight. For those few seconds between leaving the roof and hitting the ground, the falling person would feel weightless. Completely, genuinely weightless. As if gravity had simply switched off. This seems like a small observation. Of course, a falling person feels weightless. You've experienced something similar on a roller coaster during that brief moment at the top of a drop, when your stomach lifts and everything seems to float. You might have felt it jumping off a diving board, or in an elevator when the cable slips just slightly. These moments of weightlessness are common, but Einstein saw something in this everyday experience that no one else had seen. He saw a principle, a deep, structural principle that would eventually become the foundation of an entirely new theory of gravity. What Einstein realized was this: a person in free fall doesn't just feel weightless. A person in free fall is, for all measurable purposes, in a state identical to floating in empty space with no gravity at all. Not approximately identical, not similar. Identical. There is no experiment the falling person could perform, no measurement they could take, no instrument they could read that would tell them whether they were falling in a gravitational field or floating freely in the complete absence of gravity. The two situations are physically indistinguishable. This is called the equivalence principle, and it is one of the most important ideas in the history of physics. Let's explore it carefully because it's the key to understanding why you don't feel Earth's orbit around the sun. Imagine you're in a small sealed room with no windows. You're floating. Your feet aren't touching the floor. Objects released from your hand just hover in place beside you. A drop of water squeezed from a bottle forms a perfect sphere and floats in midair. You feel no weight, no up, no down, nothing pulling you in any direction. Now, there are two possible explanations for this experience. The first is that you're in deep space, far from any planet or star, where gravity is essentially zero. The second is that you're in a room that's falling freely in a gravitational field. Maybe the room was dropped from a great height and is plummeting toward the ground. Maybe the room is in orbit around a planet, continuously falling but never hitting the surface. In both cases, your experience is identical. You float. Objects float around you. Nothing feels like it's being pulled anywhere. Einstein's claim was that no experiment conducted inside that room could ever distinguish between these two scenarios. Not because our instruments aren't good enough, but because the two situations are fundamentally physically the same. Free fall in a gravitational field, and the absence of gravity are indistinguishable from the inside. Now imagine the opposite scenario. You're in the same sealed room, but this time your feet are firmly on the floor. You feel your normal weight. Objects fall when you drop them. Everything behaves exactly as it does in your living room on Earth. Again, there are two possible explanations. The first is that you're on the surface of a planet, with gravity pulling you downward. The second is that you're in deep space, far from any gravitational source, but the room is being accelerated upward by a rocket engine at 9.8 meters per second squared, which is the same rate as Earth's gravitational acceleration. The floor of the room pushes up against your feet, and you feel this as weight. Objects released from your hand accelerate toward the floor, not because of gravity, but because the floor is accelerating upward to meet them. Einstein's claim was that these two scenarios are also indistinguishable from the inside. No experiment could tell you whether you're feeling gravity or feeling the acceleration of a rocket. They produce exactly the same effects. The same forces on your body, the same trajectories for dropped objects, the same readings on every instrument. Gravity and acceleration are equivalent. That's the equivalence principle. Now, this might sound like a philosophical curiosity, but it has enormous practical consequences. And the most important consequence for our question tonight is this. If free fall is equivalent to the absence of gravity, then anything in free fall should feel no gravitational effects whatsoever. Not just approximately none, exactly none. Every gravitational acceleration should vanish from the perspective of the freely falling observer. And Earth is in free fall around the sun. Let's think carefully about what Earth's orbit actually is. Earth moves through space in an approximately elliptical path around the sun. The sun's gravity pulls on the Earth, and this pull curves Earth's path from what would otherwise be a straight line into a closed orbit. This is centripetal acceleration directed toward the sun. It's real acceleration, Earth's velocity is constantly changing direction, bending inward, curving around the sun month after month, year after year. But here's the critical fact. This acceleration is caused entirely by gravity, and gravity has a unique property that no other force possesses. Gravity accelerates everything equally. This is something Galileo demonstrated over 400 years ago when he showed, contrary to Aristotle's teaching, that heavy objects and light objects fall at the same rate. Drop a hammer and a feather in a vacuum, and they hit the ground at exactly the same time. This isn't just approximately true for similar objects, it's exactly true for all objects regardless of their mass, their composition, their size, their shape, their temperature, or any other property. A grain of sand in a battleship, released from the same height in a vacuum, accelerate downward at exactly the same rate. This is an extraordinary fact about gravity, and it's actually quite strange when you think about it. Other forces don't work this way. If you push a heavy object and a light object with the same force, the light object accelerates faster. That's Newton's second law. Force equals mass times acceleration. More mass means less acceleration for the same force, but gravity somehow compensates for mass perfectly. A more massive object feels a proportionally stronger gravitational pull, and this extra pull exactly cancels the extra inertia from its greater mass. The result is that all objects, regardless of mass, accelerate at the same rate in a gravitational field, always, without exception. Newton noticed this and included it in his framework, but he had no deep explanation for why it was true. It was just a coincidence in his theory, a fact about how nature happened to work. Einstein saw it differently. He saw it as a clue. If gravity accelerates everything equally, then in a freely falling frame, everything accelerates together, and the gravitational acceleration disappears from the inside. That's not a coincidence. That's a principle. That's the equivalence principle. Let's apply this to Earth's orbit. The sun's gravity pulls on the Earth, but it doesn't just pull on the planet as a whole, it pulls on every individual atom of the planet separately. Every atom of rock in the mantle, every molecule of water in the oceans, every nitrogen molecule in the atmosphere, every cell in your body, every proton and neutron in every atom of your being. The sun's gravity reaches inside you and pulls on each particle individually, and it pulls them all with the same acceleration. Not approximately the same, exactly the same. This is what makes gravity so fundamentally different from other forces. If you're in a car that turns sharply to the left, you feel yourself pushed to the right. But what's actually happening is that the car, through the friction between the tires and the road, is accelerating to the left. The car seat pushes your body to the left, but your internal organs and the fluid in your inner ear resist this change in motion because of their inertia. There's a mismatch. The outside of your body is being pushed by the seat, while the inside of your body is trying to continue in a straight line. That mismatch, that differential between the acceleration of different parts of your body, is what you feel as a force pushing you sideways. Your body detects it because it's transmitted from the outside in. The seat pushes your back pushes your organs, and each step in that chain involves a tiny delay and a tiny compression. You feel the squeeze. Gravity doesn't work this way. Gravity doesn't push from the outside. It reaches inside and pulls on every single atom individually and equally. There's no chain of transmission from outside to inside. There's no mismatch between how fast your skin accelerates and how fast your organs accelerate. There's no compression, no squeezing, no differential. Every part of you accelerates at exactly the same rate at exactly the same time. From the inside, from the perspective of your body's sensors, this is indistinguishable from not accelerating at all. This is why you don't feel Earth's orbital acceleration around the sun. The sun's gravity pulls on you and on the ground beneath your feet, and on the atmosphere above you, and on every grain of sand on every beach, and every drop of water in every ocean, all with the same acceleration. Everything on Earth falls toward the sun together, in perfect unison. There is no relative acceleration between you and your surroundings. And since your body can only detect relative acceleration, the difference between how fast you're accelerating and how fast the things touching you are accelerating, you detect nothing. The orbital acceleration is there, it's real, it's measurable from outside, but from inside Earth's frame, it has been perfectly erased by the universality of gravitational acceleration. This is free fall. Earth is in free fall around the sun, not falling downward, not falling in the direction you normally think of as falling, but falling nonetheless. Earth is perpetually falling toward the sun, pulled inward by gravity, but moving forward fast enough that by the time it has fallen a certain distance inward, it has also moved far enough forward that the sun's surface has curved away beneath it. The result is that Earth never gets closer to the sun. It just keeps falling around it endlessly in a closed orbit. And inside this falling frame, the sun's gravitational acceleration vanishes completely from experience. The best modern demonstration of this principle happens on the International Space Station. Astronauts on the ISS float. They drift through the cabin, their food floats in front of them, water forms perfect spheres in midair. Most people think this happens because the ISS is in space and there's no gravity up there. But this is wrong. The ISS orbits at an altitude of roughly 250 miles above Earth's surface. At that altitude, Earth's gravitational field is still about 90% as strong as it is on the ground. The astronauts are very much in a gravitational field. Gravity has not gone away. It's almost as strong as what you feel right now sitting in your chair. The astronauts float because they're in free fall. The ISS is falling toward the Earth continuously. It's moving forward fast enough, about 17,500 miles per hour, that its curved falling path matches the curvature of the Earth below it. It falls and falls and falls, but the ground curves away at exactly the same rate, so the station stays at the same altitude. It's a perpetual free fall that never reaches the ground. And inside this free fall, the astronauts experience weightlessness. Not because gravity is absent, but because they and the station and the air inside the station and every object on board are all falling together at exactly the same rate. There is no relative acceleration between the astronauts and their surroundings. Their bodies detect nothing. They float. This is exactly what's happening to you right now with respect to the sun. You are falling toward the sun. The Earth and everything on it is falling toward the sun at every moment. The sun's gravity is pulling you sunward right now, accelerating you, changing the direction of your motion. But you don't feel it because everything around you is falling at the same rate. There's no relative motion. There's no differential force. From inside your reference frame, The sun's gravitational acceleration simply doesn't exist as a felt experience. Now, I said earlier that the sun's gravity pulls on every part of the Earth equally. That's almost true, but not perfectly true. And the tiny imperfection is worth mentioning because it actually produces an observable effect. The sun's gravity is slightly stronger on the side of Earth facing the sun, and slightly weaker on the side facing away. This is because gravity gets weaker with distance, and one side of the Earth is about 8,000 miles closer to the sun than the other side. This difference in gravitational pull across the width of the Earth is called a tidal force. Tidal forces are real. They're the same kind of force from the moon's gravity rather than the sun's that causes ocean tides on Earth. The moon's gravity pulls slightly harder on the near side of the Earth than on the far side, and this differential stretches the Earth slightly along the Earth-Moon line, creating two bulges of water that we experience as high tides. But here's the thing. While tidal forces from the moon are strong enough to move entire oceans, the tidal force from the sun across the width of a human body is absurdly tiny. The difference in the sun's gravitational pull between your head and your feet amounts to roughly 1/100th of a trillionth of a G. That's a force so small that it's completely unmeasurable by any sensor in your body. Even the most sensitive scientific instruments would struggle to detect such a force over a distance of 6 feet. So, while the cancellation of the sun's gravity in free fall isn't mathematically perfect, it's so close to perfect that the remaining tidal effect is billions of times below the threshold of human perception. Let's extend this understanding even further. Because Earth isn't just in free fall around the sun. The entire solar system is in free fall around the center of the Milky Way galaxy. The sun and all its planets orbit the galactic center at roughly 490,000 miles per hour. This is gravitational acceleration, a continuous change in direction as we curve around the galactic center over the course of 225 million years. And we don't feel it. We don't feel it for exactly the same reason we don't feel the sun's gravity. The Milky Way's gravity pulls on every atom of the solar system equally. Everything falls together. There's no differential, no relative acceleration within the system. The galactic gravitational acceleration vanishes from inside our frame just as completely as the sun's does. And it goes further still. The Milky Way is falling toward the Andromeda Galaxy. The local group of galaxies is being pulled toward the Great Attractor and the Shapley supercluster. At every scale, from orbiting a star to orbiting a galactic center, to falling through the large-scale structure of the cosmos, the same principle applies. Gravitational acceleration is universal. It affects everything equally, and therefore it vanishes from the inside. Free fall is undetectable, no matter how fast you're falling, no matter how strong the gravitational field, no matter how dramatic the acceleration appears from the outside. This is one of the deepest and most beautiful results in all of physics. It tells us that gravity is not like other forces. It doesn't push or pull in a way that can be locally detected. It curves the paths of objects through space-time, but those objects, from their own perspective, are simply following the most natural path available to them. They're not being pushed, they're not being pulled, they're just moving, following the contours of curved space-time, and experiencing no force whatsoever. Einstein formalized this into his general theory of relativity published in 1915. In general relativity, gravity is not a force at all. It's the curvature of space-time caused by the presence of mass and energy. Massive objects like the sun curve the space-time around them. Other objects moving through this curved space-time follow curved paths, not because a force is acting on them, but because space-time itself is curved. The paths they follow, called geodesics, are the straightest possible paths through curved space-time. In a sense, objects in gravitational freefall are moving in perfectly straight lines. It's just that the space they're moving through is bent, so what looks like a curved orbit from the outside is actually the straightest possible path from the object's own perspective. This is a radical reimagining of what gravity is. In Newton's framework, gravity was a force that acted instantaneously across empty space. The sun pulled on the Earth with a force, and the Earth pulled back on the sun. This force caused acceleration, and the acceleration curved the orbit. In Einstein's framework, there is no force. The sun's mass curves the space-time around it. The Earth moves through this curved space-time along the straightest path available, a geodesic, and this path happens to be an ellipse. From the Earth's perspective, there's no acceleration because it's following a geodesic. It's the natural, unforced motion through curved space. From an outside perspective, looking at the geometry, the Earth's path is curved. But from the inside, from the perspective of a freely falling observer riding along with the Earth, the path is perfectly straight through locally flat space-time. There is no force, no acceleration, no sensation, just smooth, unforced motion along the natural geometry of the universe. This is why the equivalence principle works so perfectly. In general relativity, free fall isn't just similar to the absence of gravity. Free fall is the absence of gravity locally. The gravitational field isn't something that acts on you in free fall. It's something you're moving through without resistance. The curvature is in the space-time around you, not in any force applied to you. You're like a marble rolling along a curved surface. The marble doesn't feel the curvature, it just follows the surface, moving in what it experiences as a straight line. Only someone looking at the surface from above can see that the path is curved. This view of gravity has been confirmed by over a century of increasingly precise experiments. General relativity predicted that gravity would bend light, and Arthur Eddington confirmed this during the 1919 solar eclipse by observing stars whose light passed near the sun. Their apparent positions were shifted exactly as Einstein predicted. General relativity predicted that time would run slower in stronger gravitational fields, and this has been confirmed using atomic clocks at different altitudes. A clock on a mountaintop runs very slightly faster than an identical clock at sea level, because it's in a weaker gravitational field. This effect is small but measurable, and GPS satellites must account for it. Without corrections for gravitational time dilation, GPS navigation would accumulate errors of several kilometers per day. General relativity predicted gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects. In 2015, the LIGO Observatory detected gravitational waves for the first time, produced by the merger of two black holes over 1 billion light-years away. The signal matched Einstein's predictions with extraordinary precision. General relativity predicted the existence of black holes, regions where space-time is so severely curved that nothing can escape. In 2019, the Event Horizon Telescope collaboration produced the first direct image of a black hole shadow in the galaxy M87. Every test, every observation, every experiment has confirmed Einstein's picture. Gravity is not a force pulling you inward. It's the curvature of space-time through which you fall freely. And in free fall, you feel nothing because there's nothing to feel. You're just following the geometry of the universe. So let's restate the answer to our central question with full precision. Why don't you feel the Earth moving at 67,000 miles per hour? There are 2 layers to the answer. The first layer is Galilean relativity. Constant velocity motion is undetectable. If Earth were moving in a perfectly straight line at constant speed, you wouldn't feel it because constant velocity produces no acceleration, and your body only detects acceleration. This explains why speed itself is invisible. The second layer is the equivalence principle and general relativity. Earth's orbit is not constant velocity motion. It involves continuous centripetal acceleration toward the Sun. But this acceleration is gravitational, and gravitational acceleration is universal. It affects everything equally. You and the ground and the air and the oceans all accelerate together in perfect unison, falling toward the Sun as one. From inside this shared free fall, the acceleration vanishes. It's not just hard to detect. It's not just too small to notice. It's physically absent from your frame. The freely falling frame is an inertial frame, a frame with no net acceleration. Because gravity has been geometrically absorbed into the curvature of space-time, rather than acting as a local force. Both layers work together to create the experience of perfect stillness. The constant speed component of Earth's motion is undetectable by Galilean relativity. The change in direction component, the centripetal acceleration, is undetectable because of the equivalence principle. Together, they make Earth's entire orbital motion completely invisible from the inside. 67,000 miles per hour vanishes without a trace. But there's still one more layer to this story. One more twist that makes the whole picture even more extraordinary. Because if free fall is the natural, unaccelerated state, then what about the one acceleration you do feel? What about the one force that's been pressing on you your entire life? So constant and so familiar that you've never thought to question it? What about the sensation of weight? The feeling of the ground pressing up against your feet, the chair pushing against your back. If free fall is the state of no acceleration, then standing on solid ground is the state where you are being accelerated. And that changes everything about how we understand what it means to be still, what it means to move, and what the ground beneath your feet is actually doing to you right now. But the same logic doesn't stop at the sun. It extends outward to every gravitational orbit we participate in, and to the expansion of the universe itself. Space is stretching, carrying galaxy clusters apart. But this expansion doesn't produce any local force. It doesn't compress or stretch anything on human scales. It's a geometric phenomenon operating on scales so vast that within our solar system, our galaxy, even our local group, its effects are negligible. You could no more feel the expansion of the universe than you could feel the curvature of the Earth by looking at the floor of your kitchen. Every layer of motion we catalogued at the start of this journey now has its explanation. Earth's rotation involves a tiny centripetal acceleration, but as we saw, it amounts to 1/3% of surface gravity, completely lost in the sensation of your own weight. Earth's orbit is gravitational free fall, invisible for the reasons we've just explored. The solar system's orbit around the galaxy and the Milky Way's drift through the cosmos obey the same principles at ever larger scales. Constant velocity is undetectable. Gravitational freefall is undetectable. The rules don't change just because the numbers get bigger. Not a single one of these motions registers. The physics erases every one of them from the inside. Now, there's one more twist in this story, and it's perhaps the most mind-bending of all. We've been talking about how you don't feel the Earth's motion through space. But what about the one motion you do feel? The one sensation of acceleration you experience every single moment of your life. So constantly that you've stopped noticing it? Gravity. Or rather, what you perceive as gravity. When you stand on the ground, you feel your weight. You feel the floor pressing up against your feet. You feel the chair pressing up against you when you sit. You feel a downward pull, constantly, relentlessly, all day, every day. You felt it since the moment you were born. It's so constant and so familiar that you think of it as simply the way things are. But here's what Einstein showed us. That sensation, that feeling of weight, is not the feeling of being pulled down by gravity. It's the feelings of being pushed up by the floor. This sounds strange, so let me connect it to what we've already learned. We showed that in general relativity, objects in free fall are following geodesics, the straightest possible paths through curved space-time. No force acts on them. They feel nothing. That's why astronauts float, and why you don't feel Earth's orbit. But you're not in free fall right now. You're standing on the ground, and the ground is preventing you from following your natural geodesic path. It's pushing you upward, away from the center of the Earth, accelerating you upward at 9.8 meters per second squared. You feel this upward acceleration as weight. What you call feeling gravity is actually feeling the ground accelerating you away from a free fall trajectory. Let's make this as concrete as possible, because this idea is so counterintuitive that it needs more than a quick explanation. It needs to be felt. Imagine you're standing in an elevator on the 40th floor of a building. The cable snaps, the elevator begins to fall. In that instant, something extraordinary happens. Your weight vanishes, not gradually, instantly. Your feet lift gently off the floor. Your arms float upward. The keys in your pocket drift out and hover beside you. A coin you were holding doesn't drop. It just stays where it was, suspended in the air next to your hand. You are weightless. Completely, perfectly weightless, in exactly the same way as an astronaut on the space station. Now, here's the question that reveals everything. Did gravity turn off? Obviously not. Gravity is what's pulling the elevator downward. Gravity is very much present. It's the entire reason you're falling. So why do you feel weightless? Because the floor is no longer pushing up against you. That's it. That's the only thing that changed. One moment the floor was pressing against your feet, accelerating you upward, and you felt weight. The next moment the floor dropped away, the upward push disappeared, and the sensation of weight vanished with it. What you lost wasn't gravity. You lost the floor's resistance to gravity. And the moment that resistance disappeared, so did every sensation you associated with gravity. This tells you something profound about what weight actually is. Weight is not the sensation of being pulled down. Weight is the sensation of being pushed up. It's the floor fighting against your natural tendency to fall. Remove the floor and the sensation disappears, even though gravity is just as strong as it was a moment ago. The gravity didn't change. Your relationship to free fall changed. Now think about this from the other direction. Imagine you're floating in deep space, far from any star or planet. There's no gravity. You're weightless. You're following a geodesic through perfectly flat space-time. Now someone straps a rocket to the floor of your room and fires it. The rocket accelerates the room upward at 9.8 meters per second squared. Suddenly the floor rushes up to meet your feet. You feel heavy. Objects released from your hand fall to the floor. Water pours downward from a cup. Everything behaves exactly as it does in your living room on Earth. You feel weight. You feel a downward pull, but there's no gravity. There's no planet beneath you. There's nothing pulling you down at all. What you're feeling is the floor pushing you up, accelerating upward into you. And that sensation is identical to what you feel standing on Earth right now. Einstein's great insight was that these two experiences, standing on Earth and being accelerated by a rocket in empty space, are not just similar. They are the same thing. Both involve a surface pushing you away from your natural free-fall trajectory. Both produce the sensation of weight, and there is no experiment you could perform inside either room that would tell you which one you're in. Here's something that makes this even more tangible. If you have a smartphone, it probably has an accelerometer inside it. This is a tiny sensor that measures acceleration. Right now, if your phone is sitting on a table, that accelerometer is registering an acceleration of 9.8 meters per second squared, pointing upward, not downward, upward. The sensor is telling you that the table is pushing the phone upward. If you pick up the phone and drop it during the brief moment it's in the air, the accelerometer reads 0. Exactly 0. No acceleration at all. The phone in free fall, the phone that's obviously moving, falling toward the ground, registers no acceleration. The phone sitting still on the table registers 9.8 meters per second squared. The still phone is accelerating. The falling phone is not. This seems backward. It seems like the falling phone should be the one accelerating, and the phone on the table should read 0. But the accelerometer doesn't lie. It's measuring exactly what it should. The phone on the table is being accelerated upward by the table. The phone in free fall is following a geodesic, the natural path through curved space-time, and experiencing no force at all. The accelerometer confirms what general relativity predicts. Free fall is the unaccelerated state. Being held up by a surface is the accelerated state. Think about what this means for your daily life. Every morning when your alarm goes off and you drag yourself out of bed, that heaviness you feel, that resistance to getting up, isn't laziness, and it isn't just the desire for more sleep. It's the real physical sensation of being accelerated upward by your mattress all night long, and then by the floor when you stand. Your body has been pushed away from its natural geodesic for your entire life. The fatigue you feel after standing all day isn't just muscle strain. Part of it is the continuous acceleration your body experiences from the floor pressing against your feet hour after hour. When you jump, there's a brief moment in the air where you're weightless, truly weightless, just like the astronauts. It's only a fraction of a second, but during that time, your body is in free fall. You're following a geodesic. No force acts on you. Then the ground catches you again, and the acceleration resumes. Every jump is a tiny holiday from acceleration. Every time you float in a pool and feel that relief, that lightness, part of what you're experiencing, is a reduction in the contact force accelerating you. The water supports you more gently than the ground does, distributing the upward push across your whole body rather than concentrating it at your feet. The physics is the same, but the sensation is softer. When you ride a roller coaster and experience that moment of weightlessness at the top of a hill, your body isn't being tricked. It's experiencing genuine free fall. For that brief moment, the track isn't pushing the car upward. The car is following a ballistic arc, a geodesic, and you're going along with it. Your stomach floats because your organs are in free fall, following their own geodesics, no longer being pushed upward by the seat beneath you. The moment the car comes back into contact with the track, and the track pushes upward again, the weight returns. The acceleration resumes. The free fall ends. All of these everyday experiences confirm the same principle. What you feel as weight is not gravity pulling you down, it's the ground pushing you up. Gravity itself is silent. It produces no sensation. It's just the curvature of space-time, and you follow that curvature naturally, effortlessly, without feeling a thing. The only time you feel something is when a surface gets in the way and forces you off your natural path. This is worth letting sink in. In the framework of general relativity, the person who is accelerating is you, standing on the ground. The person in free fall, the astronaut floating on the space station, is the one who is not accelerating. Free fall is the natural state. Being supported by a surface and prevented from falling is the state that involves acceleration, the state that produces sensation. So when someone asks, why don't we feel the Earth moving at 67,000 miles per hour? The deepest answer is this: we don't feel it because there's nothing to feel. Motion at constant velocity is physically undetectable. Gravitational orbital motion is free fall, and free fall is the natural, unaccelerated state of motion through curved space-time. The only thing you actually feel is the ground pushing you upward, preventing you from freely falling. That's the one acceleration in your life that's real and persistent. Everything else, the rotation, the orbit, the galactic journey, the cosmic drift, all of it is either constant velocity or free fall, and both are invisible from the inside. This has a philosophical dimension that's worth pausing on. We glimpsed earlier that motion is a relationship, not a property. But now, after understanding free fall and curved space-time, we can see the full depth of that idea. There is no cosmic background against which you can measure your true speed. There are only relative speeds between different things. The Earth moves at 67,000 miles per hour, relative to the Sun. But relative to itself, Earth isn't moving at all. And both of these statements are equally true, equally valid, equally physical. We established earlier that no experiment can reveal absolute velocity because the concept doesn't exist. But now we can appreciate just how deep that truth runs. It isn't merely that our instruments are limited. The universe itself contains no preferred frame, no cosmic stage, no background grid. Even the cosmic microwave background, the closest thing to a universal reference, doesn't earn special status. The laws of physics work the same in every inertial frame. The question, how fast am I really moving, simply has no answer. You move at different speeds relative to different things. That's all there is. The universe is democratic about motion, and it always has been. It's worth stepping back for a moment and appreciating the intellectual journey that brought us here. Because the understanding we've arrived at tonight didn't come easily. It took 4 centuries and 3 of the greatest minds in the history of science, each building on the work of the one before, each peeling back a layer of illusion to reveal something deeper about reality. Galileo was the first. In the early 1600s, he destroyed the Aristotelian idea that motion requires a continuous force. He showed that constant velocity is the natural state, that rest and motion are indistinguishable from the inside, and that the physics inside a moving ship is identical to the physics on dry land. This was the first layer. Galileo showed us that speed is invisible, that you cannot feel constant motion, that the universe doesn't distinguish between moving and standing still as long as the motion doesn't change. This was revolutionary. For nearly 2,000 years, everyone had assumed the opposite. Galileo proved them wrong with nothing more than a thought experiment and careful reasoning. Newton came next. In 1687, he published the Principia, one of the most important books ever written. Newton took Galileo's insight and formalized it into precise mathematical laws. He showed that forces don't cause motion. Forces cause changes in motion. Forces cause acceleration. This was the second layer. Newton gave us the language to understand exactly what our bodies detect and what they don't. We feel forces. We feel acceleration. We don't feel velocity. Newton also gave us the law of universal gravitation, explaining that the same force that pulls an apple from a tree holds the moon in orbit around the Earth and the Earth in orbit around the sun. This unified the heavens and the Earth for the first time, showing that the same physics applies everywhere. But Newton left a mystery. In his framework, gravity was a force that reached across empty space, pulling objects toward each other instantly. He had no explanation for why gravity accelerates all objects equally, regardless of mass. He accepted it as a fact but couldn't explain it, and his theory contained an assumption that would eventually be overturned. Newton believed in absolute space and absolute time. He believed there was a universal frame of rest against which all motion could be measured. He was wrong about that, but no one knew it for over 2 centuries. Einstein completed the revolution. First with special relativity in 1905, he showed that there is no absolute space, no absolute time, no preferred frame of rest. All inertial frames are equivalent. Motion is purely relative. Then, with general relativity in 1915, he went further. He showed that gravity is not a force at all. It's the curvature of space-time. Objects in free fall aren't being pulled. They're following the natural geometry of the universe. And the sensation of weight, the thing we feel every moment of our lives, isn't gravity pulling us down. It's the ground pushing us up, preventing us from following our natural path through curved space-time. This was the third and deepest layer. Each of these thinkers peeled back one layer of the illusion. Galileo showed that constant motion is invisible. Newton showed that only acceleration is felt. Einstein showed that gravitational acceleration isn't felt either because it isn't really acceleration at all. It's just the natural motion through curved space-time. And the one thing we do feel, the weight beneath our feet, the pressure of the chair against our back, that's not gravity. That's a surface accelerating us away from free fall. The progression is beautiful. Each insight builds on the previous one. Each one is more radical, more counterintuitive, more profound, and together they give us a picture of reality that is nothing like our everyday intuition, but one that has been confirmed by every experiment ever performed. The universe works this way, not approximately, not roughly, but exactly. And the result is that you can be moving at 67,000 miles per hour and feel absolutely nothing, because the universe is built to make that motion invisible. And this is why 67,000 miles per hour feels like zero. Because in the most fundamental sense, from the perspective of the physics that governs your body and your sensory experience, it is zero. You are at rest in your own reference frame. Always have been. Always will be. The sun is the one that's moving. From your perspective. And from the sun's perspective, you're the one moving. Both perspectives are correct. Neither is more real than the other. This brings us to a final and somewhat startling realization. The sensation of stillness that you feel right now, that perfect calm, that absence of motion, is not an illusion. It's not your brain being tricked or your senses being overwhelmed. It's an accurate reflection of the physics of your situation. From your inertial frame, you are not accelerating through space. You are at rest. The laws of physics confirm this. Einstein's theories confirm this. Decades of experimental evidence confirm this. Your feeling of being still is correct. The only motion you truly feel, the only acceleration your body genuinely detects, is the one you've been feeling in your entire life without ever thinking of it as motion. The floor pushing you upward at 9.8 meters per second, squared, preventing you from falling freely through the curved space-time around Earth. That's not you feeling the Earth's rotation. That's not you feeling the orbital velocity. That's you feeling the ground interrupting your natural state of free fall. And in the framework of general relativity, the ground accelerating you upward is the only real acceleration in your daily life. Everything else, every cosmic velocity, every orbital trajectory, every galactic drift, is either constant velocity or free fall. And those are undetectable by definition. So the next time someone tells you that the Earth is flying through space at 67,000 miles per hour, you can smile and nod and know something wonderful. You can know that the reason you don't feel it isn't because the number is wrong or because your senses are limited. It's because the universe is built in such a way that motion itself is relative, that constant velocity is indistinguishable from rest, and that gravitational orbits are free fall, the most natural and unaccelerated state of all. The stillness you feel right now isn't a failure to perceive reality. It is reality, viewed from the inside. The universe isn't hiding its motion from you. It's showing you something deeper. That motion, in the absolute sense, doesn't exist. Only relationships between things exist. And from the relationship that matters most, the one between you and everything moving with you, you are at perfect rest. 67,000 miles per hour is real, measured from the sun. 1.3 million miles per hour is real, measured from the cosmic microwave background. 0 miles per hour is real, measured from the frame you actually live in. And 0 is the one your body reports, because 0 is the one that's physically true for you. The deepest lesson of all this isn't about speed or orbits or reference frames. It's about perspective. The universe looks different depending on where you stand. What feels like terrifying speed from one vantage point feels like absolute stillness from another. And both are correct. Both are true. The universe contains all these perspectives simultaneously and doesn't prefer any of them. You are hurtling through space at unimaginable speeds, and you are perfectly, completely, genuinely still. Both of these things are true at the same time. And the fact that they can both be true, the fact that physics allows for this, is one of the most beautiful and profound things about the nature of reality. The next time you're lying on your back looking up at the stars, remember this. You're not really lying still on a moving planet. You're at rest in your reference frame while participating in a cosmic ballet of motions that are all invisible from the inside. The stillness you feel is real. The speed is also real. And the universe is generous enough to let both be true at once. That's not a contradiction. That's physics. That's how reality works at the deepest level we've ever been able to probe. And it took humanity's greatest minds, from Galileo to Newton to Einstein, centuries of thought and argument and experiment to arrive at this understanding. The understanding that stillness and incredible speed are not opposites. They are perspectives on the same reality, two ways of describing the same event, equally valid, equally real, coexisting without conflict. So, sleep well tonight. You're racing through the cosmos at millions of miles per hour, and you're perfectly, beautifully still, both at once. That's not a paradox. That's the universe being exactly what it is. And perhaps that's the most remarkable thing of all. Not the speeds themselves, not the physics, not even the elegance of Einstein's equations, but the fact that the universe is built in such a way that the deepest truths about motion and gravity are hidden from our direct experience. We live our entire lives feeling the ground beneath us, interpreting that sensation as the pull of gravity, believing ourselves to be stationary on a motionless surface. None of those interpretations are quite right. The ground is accelerating us. The pull we feel is a push, and our planet is anything but motionless. But the universe has arranged things so that none of this matters to your daily experience. The physics works perfectly whether you know about it or not. The coffee stays in your cup whether you understand reference frames or not. The sun rises and sets whether you know about orbital freefall or not. The universe doesn't require your understanding in order to function. But understanding it changes something. It changes you. Not in a way that makes the coffee taste different or the sunrise less beautiful, but in a way that adds a layer of depth to everything. When you feel your weight in the morning and groan at the effort of getting up, you can know that you're feeling the only real acceleration in your life. The ground pushing you away from your natural state of weightless free fall. When you look out the window and see the stillness of a quiet afternoon, you can know that behind that stillness is a planet racing around a star at 18 miles per second. A star orbiting a galaxy at 140 miles per second. A galaxy drifting through the cosmos at hundreds of miles per second. All of it invisible, all of it silent, all of it perfectly hidden by the structure of physics itself. And when someone asks you why you can't feel any of it, you'll have the answer. Not a simple answer, not a one-sentence explanation, but a real answer. One that touches on Galileo's ships and Newton's laws, and Einstein's curved space-time, and the extraordinary fact that falling and floating are the same thing. The universe is generous with its secrets, but only if you ask the right questions. Why don't I feel the Earth moving? Sounds like a simple question. But the answer reaches into the deepest foundations of physics. It connects your everyday experience of sitting still in a room to the most profound ideas about the nature of space, time, gravity, and reality. It connects the feeling of weight under your feet to the curvature of space-time around a planet. It connects the silence of a quiet room to the cosmic ballet of orbits and free falls happening all around you at every moment. That's the power of a good question. It starts with something obvious and ends somewhere extraordinary. And this particular question, the one about why 67,000 miles per hour feels like zero, ends in one of the most beautiful places in all of physics. It ends with the realization that stillness and motion are not opposites, that the universe has no preferred frame, that gravity is geometry, not force, and that the one thing you feel most constantly, most reliably, most inescapably, the weight of your own body, is not what you think it is. It's not the universe pulling you down, it's the ground holding you up. And the moment it stops, you fly. Thank you for staying with me through this exploration. If you found it valuable, a like or subscribe would mean a great deal. It helps me keep making these deep journeys into the science that shapes our reality. And remember, the stillness you feel right now is not a lie your body is telling you. It's one of the deepest truths physics has ever uncovered. You are at rest, you are flying, and the universe doesn't see a difference. Good night.